Hey everybody, Dr. A here, and in this video we're going to be providing some background information on frame internal loading. So let's go ahead and get started. The first sentence I have here basically states that frame internal loading is basically going to follow the same process as we saw with beams, okay? And what does that process deal with? Well, basically it uses the method of sections to pass a cut section through the point of interest in the frame member, okay? So for example, let's say that we have a two-member frame like this, and let's say that you have a pin connection down here and a roller connection here, and let's say that we have some kind of loading on here, okay? Some kind of arbitrary loading. All right, and let's say that you want the internal loads at this point right here. I'm going to call it point B, okay? So what we would do is we would do method of sections, and we would put a cut section through that point, and we would separate this frame into one of two free body diagrams and analyze one of them. So for example, if we were to continue working with this particular frame, you can break this off here, and you've got that cut at B. Here's part of that internal load that's hanging out there, W. Here's that P, and here is that normal force right here. I'm going to call it NR for normal reaction. And then at this cut section, you're going to have an internal normal force, you'll have an internal shear force, and you're going to have an internal bending moment. So you could analyze this upper free body diagram above the cut, or you could analyze the lower free body diagram, which I'm going to color code here. I'm going to draw down here, and on this lower free body diagram, you've got an X and a Y reaction here, and this is the other side of the cut, and you've got the normal force in the opposite direction, shear force, and bending moment here, okay? And so remember, from method of sections, does it matter if we analyze this lower free body diagram or this upper free body diagram? No, it really doesn't. You can analyze either one, and it also follows the same process of when we need to determine external support reactions. So, if you do method of sections, the free body diagram that you're analyzing, if it includes an external support reaction, then you would have to get those first, okay? So generally, same process that we saw with a beam, all right? Now, let's talk about internal load functions for frames. Well, for internal load functions in a frame, we can define a new origin and location variable X after every abrupt change. Now, when we say abrupt changes could be the application of a load. It could be a change in a cross-section property, a change in material property, or a change in geometry, okay? So we can define a new origin and location variable X after every abrupt change. Now, we must define a new location variable after each geometric change. Now, when I say geometric change, I mean a actual change in dimension of geometry, okay? Not necessarily a change in cross-section or material property, but a geometric change. So if I come over here and let's say that I'm interested in, again, the internal loading functions of a frame, okay? So let's say that I have this kind of two-member frame here again, and let's say that, I've got a pin at A, and let's say that I have this rigid connection at B and a roller here at C, okay? And let's say I've got a point load here, P, and then let's say I have this uniform load across the top, W, okay? So here's what we would do, okay? We would need some kind of origin and location variables. Now, a lot of times textbooks will tell you what your origin and location variable is, and some won't. In some cases, you have to define your own. So, for example, I could call point A the origin, and I could say here is x1, okay? I could then encounter this abrupt change, which the abrupt change is defined by the presence of P here, and I can define a new origin here and call this x2, okay? This one is going to be optional, all right? So you can make a note here. Defining this is an optional, okay? Now, what would be required is for us to have a new location variable at this corner B, and we can call this one x3, okay? So this one up here would definitely be a required new origin, a new location variable definition, because we have this abrupt geometric change because we're literally turning a corner here, okay? You can't just have your same x1 or x2, when you're wrapping around and you're turning a corner, okay? So that's what that means. Now, similar with beams, you have options here on how you define these. So for example, we could say, okay, here's that same frame. Here's that same frame. I got the pin at A, I got the roller at C, I got the rigid connection at B. Here's W. Here's P. Okay, what you could do is you could call this X1. That's totally fine. If a problem in a particular given statement or in a textbook does not tell you what the origin is, then you can define one yourself. If a problem does tell you what the origin is, you should use what the problem tells you to. Now, where else would I need to define a new origin and a new location variable? Well, again, need one at B. I need to go down here. This could be x2, okay? And then remember, defining a new location variable with this applied load here is optional, okay? x2 could extend all the way down here, okay? So what I would say is for this particular frame illustration, we have to have two location variables. We must have two location variables for sure. Now, we could have a third one that is defined where we have this abrupt change in loading here. So you could reasonably have three, okay? But you got to have two. And again, you got options here. What would be a third option that you could define some location variables for this kind of frame? Well, if I come back over here and I redraw this same frame, I've got P here, I've got A, I've got the uniform load here, I got C, I got that solid rigid connection B. What are some other options? Well, you could call, this X1, and then you could define X2 as coming over here. So why is this okay? Well, remember, X1, it can capture everything that's happening from A to B, okay? And then X2 can capture everything from C to B. So you still capture everything that's happening on this entire frame, okay? And remember, defining a new origin and location variable at the point where a point load exists is optional. You don't have to do that. I mean, you're still going to have to make multiple cuts, right? When you do method of sections, you're still going to have to make a cut here. You're still going to have to make a cut here and a cut here. But even when you're on AB, if you make a cut between point A and the point of load application, and then a second cut between the point of load application and point B, you can always reference that same location variable X1, okay? So that's something to think about. Now, if you're having trouble remembering what we did with beams, then I suggest you go back and look at some of my previous videos where we saw this topic for beam analysis, for internal loading of beams. It's always cleaner to start with beams and then kind of slowly work your way up to frames, okay? Now, last illustration I want to show us is what happens if we have kind of like a cockeyed frame. So let's say that we have, a cantilever frame, and let's say that we have, this frame kind of at an angle like this, and maybe we've got a point load here or something like that. And what should I do in terms of location variables? Well, again, you want to define a location variable generally along a member axis. I think that was pretty obvious from everything I drew in these three examples. We were always defining location variables along member axes. So what happens if you have a member, at an angle like this? Let's say that's at some angle theta. Well, in this case, what you're going to do is you're going to define a location variable that's along this particular axis. We can call this x1. And then, once you hit this corner, you round the corner, you call this x2. And so you still follow the same general pattern. You're defining this location variable along that diagonal angled member length. And then you hit a geometric change, which is this corner. And then you define a new location variable here. Okay, so again, this is just background information on what you're looking at for location variables. And like I've said a couple of times here, you could have a problem from a textbook that gives you the location variables already, okay? But if you don't have a location variable, if you don't have an origin or an X set of variables defined in a problem, then you're going to have to define one yourself. And this is how you can go about thinking that through, okay? So that concludes this background information on internal loading of frames. Thanks for watching, and please be on the lookout for other content like this, including some examples of this topic. All right, thanks for watching.